Welcome back to the FAST lecture series. We're going to continue to talk a little bit more about solar panels, and especially electric current and solar panels. And we're going to be talking about electricity much later on in the year. But in order to really understand how solar panels work and how thermodynamics comes into play, we really do need to understand how electric current actually works. And we've talked about this a couple times in class, but I think drawing this out and applying it to thermodynamics will help explain this a little bit better. So here is a solar panel. We've kind of blown it up. And here are the two parts that we've really talked about. This N-type silicon, which we know has too many electrons because we've doped it with phosphorus. And when you do that, you get too many electrons that are floating around in there. And then we have this P-type silicon, which, if you dope it with boron, you get too few electrons, so this one doesn't have enough. Now, when we do this, we create a net charge, or not really create, but there is a net charge that happens. So there's too few electrons over here, which means that this is going to have a positive charge, and this one's going to have a negative because there's too many electrons. And what we already know, based on the second law of thermodynamics, is that things are going to flow from a high to low concentration until they reach some kind of equilibrium. In this case, if you have too many electrons over here and too few over here, you're going to start seeing this flow of electrons that are traveling towards this p-type. So we'll label that as an electron. I am going to write all of these out just to make sure that we're clear. So we'll say that electrons are going to flow from an area of high concentration to low concentration. Now here's the difficult part. Is that when you do this, we have to assume that the p-type silicon is never going to fill up, because it's always going to have a deficit of electrons. It's always going to have too few. We have to assume that. We also have to assume that the N-type silicon is never going to run out of electrons, because it's always going to have too many. So those are two assumptions we really need to make here, that this one's never going to run out, and this one's never going to have enough. So this flow is going to be continuous. We just have to make that assumption for now. What this does is this is going to create a charge. So our p-type is positive, and then our N-type is negative. Things with a positive charge are considered a high charge. So this is going to be a high charge, and likewise that one will be low. And this is because of the first law of thermodynamics. So I'm going to make a little note down here that this has to do with the first law, that essentially you can't create or destroy energy. And in this case, the energy that we really care about is going to be this charge. What's important about this is that we can't create or destroy this charge that we've created, but it's going to just flow somewhere. All right, we know that it has to go from one place to another. So imagine that this flow of charge going from high to low, so our charge is going this way, or our electric current. So we'll label that as current, and I think we can just assume that these are current. Imagine that this flow is like a river. So that this flow of current is kind of like a river, and it's driven by these electrons that are moving this way. If we think of it like that, imagine that you have some sunlight that comes in. And that sunlight is going to knock an electron free. So that sunlight hits this N-type silicon, and now all of a sudden you have this electron that's sort of knocked out. So we'll say that's an electron. It's now been knocked out. If there's this current flowing this way because of this charge, that electron's going to get sucked up into that current. Right? It's freely floating in this current that's moving in this direction. what's going to happen is that it's going to get, this electron is going to get collected by a conductor, in this case, a wire. And that electron is then going to be carried along this conductor all the way until it reaches the thing that we're trying to power. So for example, this light bulb. So if the sunlight knocks it out, that electron gets sucked up into this current. The current is going to push it into this wire. All right, so it's kind of like a river. You get stuck in it, you have to move with the current. It's going to move this way towards the light bulb, and then once it's done doing its thing, that electron is going to circle back into the p-type silicon. And if that current's still moving, it's going to keep getting pushed back into that conductor. All right, so this, you got to again assume that this process is just going to keep going as long as there is a current there. So that's really the basis of how this works, is you got to make sure that you're keeping in mind that there is this current flowing in this direction. You're going from a high charge to a low charge. And if you knock an electron off of this silicon, it's going to get stuck in that current that's moving this way. And then that's how we can collect it, power something, and then it keeps staying in this cycle until the charge is gone. And we can talk more about this later when we get to electricity. But for right now, that's the end.